Hi, my name is Anjian Chen, and today I'm going to present on my final project on retinal vessel detection. Here's the outline of my project. I wanted to go over a type of biometrics that wasn't covered in depth during the lectures, which is retina. This project aims to identify retinal blood vessels in a training image by applying several Gabor filters and convolving them with the image data. These filter results will serve as input features for a generalized linear model where the presence of blood vessels is treated as the target variable. To evaluate its effectiveness, the model will be trained on the top half of the image and tested by the bottom half of the image, measuring its performance using sensitivity, specificity, and the receiver operating characteristic curve ROC and area under the curve AUC. This project is based on the study by Peng Yu Tang on detection of retinal vessels by Gabor transform and generalized linear model. The database used in the project is described in the study conducted by Adam Hoover, Valentina Konetsova, and M. Goldbaum on locating blood vessels in retinal image by piecewise threshold probing of a matched filter response. The database contained 20 retinal images, 20 hand-labeled vessel networks provided by Adam Hoover, 20 hand-labeled vessel networks provided by Valentina Konetsova, and 20 sample results produced by their study. Images and labels are separated to top half and bottom half, where the top half is used for training, and the results of the bottom half will be used to compare with the hand-labeled vessel networks. Here's a slice of the database, some sample retina images, and some sample retinal vessel labels from Adam Hoover, Valentina Kuznetsova, and their study. As you can see, there lies some small differences between these labels, as I'm going to compare by paired with them to the same set of the retinal vessel images and comparing the mean AUCs between them. All the images and labels described above are packages in the tar archive files containing gunzip, compressed, portable PixMap format images. So we have to perform certain data pre-processing before the experiment. Let's see the demonstration. So first of all, I have the different folders I want to put these data files to. And we first use MATLAB untar function to extract all files in the archives and organize them in different directories. Then in each directory, loop through each file, unzip the file using gunzip function, extract the name of the file, and resize the images for training. Specifically for the directory containing RGB retinal vessel images, these images should also be converted to grayscale. And for the other data directories, since they're already in binary, simply resizing them, and at last, save these files in .tip format for later retinal vessel detection. So let's go ahead and run this code to see me extracting these files. I have the tar files formats already downloaded, and let's just start running this program and do some data pre-processing. As you can see, here are some examples of the labels from, I think it's Valentina Konetsova. Like there are, these are all like hand labels to the specific blood vessels. And here is some examples from the hand labels from Adam Hoover. As you can see, there are some slight differences between these two. Let's just wait until all data is pre-processed. Here are some grayscale retina vessel images. Um, Here are some vessels labels from their study, because I'm going to compare these three different label database pairing with the same set of retina image. Okay, and we finish all the data pre-processing. As you can see, we already finished everything. Let's just close them. And then here is the main code. Just as I said, is based on the credited author Pengyu Tang. And then we start the experiment by first loading the images from the data directories. I'm using the same retina images, but pairing with different labels, and at last analyze the mean AUC for each label directory. And then we extract the features from the training image, perform multiple Gabor transforms, normalize the transform image, and then append the transform images to features, later applying it to the GLM. A Gabor filter is a Gaussian envelope modulated by a complex sigmoid. It's a linear filter used primarily in image processing and computer vision for texture analysis, edge detection, and feature extraction. It's particularly effective for capturing spatial frequency, orientation, and phase information in an image. Gabor filters highlight edges in specific directions and frequencies, which is useful for edge, texture, and pattern detection, so it is useful in biometrics. For instance, in fingerprint and iris recognition, it captures local features of the texture. In face and object recognition, it helps describe local image structure by extracting orientation specific features. And in this project, it can be used to detect retinal vessels by enhancing line-like structures that appears at various orientation and width. For a 2D Gable filter, the shape of the filter can be altered by changing the size of the envelope with sigma, the direction of the sinusoid with theta, and the frequency of the sinusoid with f. So sigma, f's, and thetas, performing the Gable transforms. And then the output features of the convoluting Gabor transform will then be fed into a generalized linear model. It is an extension of traditional linear regression that allows for response variables that have error distribution models other than a normal distribution. It is widely used in statistics and machine learning for modeling relationships between a dependent variable and one or more independent variables. In the scope of this project, the feature are the independent variables, and the locations of the vessels are the dependent variable. Gabor filters handle spatial and frequency localization, and this generalized linear model provides a statistically sound and interpretable way to classify each pixel. Thereby, the combination is lightweight compared to deep learning, but still effective. And then we're going to perform cross-validation, but since only the top half of the image is used for training and the bottom half of the image is used for testing, this is a pseudo cross-validation. Similar to the process above, first perform Gabor transform, normalize the transform image, and append the transform image to features, then feed the features to GLM, and lastly calculate the sensitivity and specificity by thresholding the output of GLMC test and comparing the threshold image with the bottom half of the label, which is treated as answer. Then plot the result ROC curve and append the computed AUC to compare the performance when paired with different label directories. So we have the pre-processed data all in these four directories, and let's just start by running this code. It might take a while because uh, I'm pairing the same set of retina images with three different label database. Yeah, just clear the previous value so that it won't be affected. And we just start to run. As you can see, we are performing different Gabor transforms to the testing image, and we can see the difference after we apply these Gabor transform on the right, comparing with the left side. It's that this process takes a while, so let's just I'm just going to let you guys watch the entire process. While this process takes like a long time, let's just stop here. As you like just these different figures of let's just pick an example. Uh, let's see. Here is like an example of an average ROC curve with AUC of 0.74, and uh, and the mean AUC for all these hand labeled vessel networks are 0.6656, 0.7560, and 0.7732 respectively, which only means moderate performance. So to enhance the performance, we can either enhance Gabor feature extraction using multiple scales and window-based features, improve GLM structure, such as adding additional features, or just do some more data augmentation, like applying slide rotations, flips, or translation to the training image to increase robustness and perform cross validation across multiple images, rather than patches from the same one to ensure generalization. And here's the reference to my project. Thank you for your attention.